Alrighty, I think I did it. Let's see here. This set up. Okay, let's see. Hopefully everything is working and the stream's on. I'm gonna get started here. So my plan is I've got a little board that needs designed that plugs in as a kind of a test manufacturing board for a much bigger board that I've been working on for a while. And so I was gonna see if I could just do that kind of on the fly live here and show my process going through building a board. Um, And so I've got a project created in KiCad here, but I don't have anything else. I guess I do have symbols and footprints, I think, for all the parts I need. We might need to make some as we go. But I'll start, maybe draw just a quick block diagram of what this needs to have on it so I don't lose track as we go here. And then we'll get started building this and wiring things up. So to get started for block diagram, so I've got there's kind of a big main connector here that'll be the connection to our board, and that goes through a little ribbon cable. And it has, for signals, let me get my other schematic pulled up as far as what the signals are on it here. So I won't show the rest of the main board, but I can have the connector up that we're interfacing with. So it's a SD card and a UART console, and then a single wire debug for a ARM microcontroller for an STM32. So let's get these up. So I've got my, actually, yeah, we'll still go with this. So we've got the main connector. See properties and that. Get a little room on the screen. So we've got our main connector. Font is gonna be way too tiny. Center that guy. Perfect. And then coming off of this, we're going to have a connector to plug in an SD card. That'll be our SD card socket there. And then we're going to have two UARTs. So there's a UART to the microcontroller, and then there's a UART to this board has a Linux system on module on it, kind of similar to like a Raspberry Pi compute module. So for that, we're going to have a USB to UART converter on that. And then instead of trying to implement the debugger on here, I'm just going to, for the first rev of this board, we're just going to plug it into an ST link. So there's going to be a ARM Cortex debug connector. Oops, missed a button there. And then I need power on this as well. So this board can also provide power to the main board, so we don't have to plug in the power connector. So there'll be a just 24 volt barrel plug input here. And so then like this USB to UART converter, that'll go out to a UART. We'll just have a little connector for the ARM Cortex. We'll have our 24 volt in, and we'll have our SD card here. And I'm just gonna kind of scooch these up here out of the way, but that's kind of gonna be our block diagram of what is going on this board. So I'm gonna start with the main connector, and I'm just gonna take the whole thing and copy it over from my other board. KiCad at least makes this sort of copy paste pretty straightforward. And then we'll start kind of renaming and hooking stuff up. So on the other board, we have both a 3.3 volt that's kind of an always on, and then there's this 3.3 volt that gets turned on and off for certain things. So those will be for different voltages. Instead of VBAT here, this is just going to be 24 volts, since we know the voltage is not connected to the battery on this end, and the no connects will be fine. And then working down from there, we're going to need an SD card. So I should, in my symbol library here, I think we have a micro SD socket, complete with footprint and everything. So we're going to grab that and flip that around so he points kind of the right direction here. And then we need a USB connector for our USB to serial while we're thinking connectors here. So I should have a USB type C. Nope, that is a plug, not a receptacle. USB type C receptacle. That's what I'm looking for. Because I could get away with just a USB 2 one, but since we've got the this one's already in my symbol, and I think I have some of these sitting in the office, so we're going to use this guy. And then moving down from there, we've got our USB to UART converter. So I did already get a symbol made for this. And this is a CP2105. So this is from Silicon Labs. It's a USB to a dual UART. I've used these Silicon Labs USB to UART converters in a few other projects and been pretty happy with them. So we're going to go put that on there. And then I need my ARM Cortex debug connector. So that will grab this, which I have one that's kind of named according to the debug standard and then references the Samtec slash GCT connector that's pretty standard on these debug interfaces. And then I need a 24 volt input. So for that, we usually have used these barrel plugs. So this one takes just a center positive barrel connector, and we'll go ahead and drop that down. I think that covers kind of all the interfaces that we will need to hook up here. Shouldn't need to reference this guy anymore, so I think we'll go full screen and we can get started wiring these up. So we've got this guy here, and then we'll just start kind of copying and pasting labels. I do need to convert, this was on a hierarchical sheet, so all these SD card ones are going to need to get swapped to just be local net labels here. So this will be SD data 3 for this top one, which it looks like usually I default these to 35 mils. I'm not sure what happened to my setup here. Let's get that changed. There we go. So SD card 3, we'll just reconnect that one. And then we'll go down the list here. This will be SD card 2. I could probably change these faster with the properties panel here than bringing up the full thing. SD card 1. And data 0. And let's see, let's do the command. And clock. You probably noticed I do have on the, when I originally designed this connector, I went ahead and put lots of grounds on here because these are pretty fast signals for these SD cards. I think it's like 50 megahertz in this particular case on the clock and stuff. So we want to keep those, give those good return paths to produce crosstalk. You can actually send pretty high frequency signals over a short enough ribbon cable as long as you've got grounds return paths. You kind of run them like almost like a differential pair between your ground and your signal with all these grounds, and gives you a nice return plane, keeps your crosstalk down. I think I'm going to leave the UARTs for just a minute as these, because these represent the direction, because I need to make sure I keep my naming and or kind of keep all the directions straight. So we'll just get the SD card ones done first. It's SD boot symbol. This is the, not a normal SD card symbol, but it's the, tells the Linux SOM on the other side whether or not it should boot off of the SD card or off of its internal flash. And then these ones are already set up correctly as symbols or as just normal labels. And yeah, we'll get to the UARTs in a bit. And then pull up just on my other screen, I've got a schematic for what an old version of this full board looked like to make sure I get this guy wired up correctly. So we need, yeah, let's copy all of our symbols here, or all of our labels, and we'll start dropping them on here. So we got data 2 can go here. This is a quick trick. If you drop one on it and then pull away, it automatically will create the line there for you without having to go into the line tool. Command 3 clock, and then there's this detect switch, but we're going to have to add a little bit of extra circuitry to get that guy all hooked up correctly. I do want, this is going to be powered off the 3.3 volt switch, so it's on when the system on module's on. And then VSS and ground will all just go straight to ground. And then for the detect, so it's active low, and this is a normally open switch. So I'm going to need a pull-up resistor on here. We'll go with like a 200K pull-up. Hook that up to the detect. And then I have this boot pin, which is the same as the detect, except for it needs to be inverted. And I don't normally have like kind of an inverter I use all the time, but I do have a just really basic MOSFET, which we can use as an inverter. So if we flip this guy around, let's see, we need flip like that. And if we put a pull up on this guy as well, switch this, figure out what the best way to lay this out on here is. Nope, I wanted to grab both of those. So if I grab a pull up resistor and then put that there, now my output be this SD boot hooks up right here, and then the detect card detect switch can go right over here, in, and this goes to ground. So when this signal is high, the MOSFET will be on, which pulls this signal low, and when this signal is low, the MOSFET will be off, and this will pull it up to 3.3 volts. So this is an inverter that doesn't look like an inverter. And so that makes a really easy way to kind of implement that boot there without needing a specific inverter. I've almost always got MOSFETs on my designs for one reason or another, so those are just a really easy way to do that. So I think that covers hooking up all of the SD card signals. So let's move on to the USB for our USB to UART converter. So first on the USB port, I want to get all my grounds hooked up and shield hooked up to the ground. Almost not, at least in my designs, there's never a good reason to make the shield be separate than ground, so that always just goes there. So I don't get these confused. I'm going to mark these will be no connects, and we're not doing super speed USB on this design, so these will all be no connects. And then since this is just a basic USB device, I'm going to double check, but I think we need 5.1K pull downs on the CC lines. So we'll pull down 5.1K pull downs. Yep, I did remember that correctly. So we'll grab some 5.1K resistors, duplicate those, and hook those up to the CC lines. And then we also need our VBus hooked up. So the cool thing with these Silicon Labs parts, at least, is that they have a little internal linear regulator to power them with. So we don't need to worry about a separate regulator. So I'm going to go double check the data sheet. I'll pull that over here for what this is supposed to look like when it's hooked up. They've got somewhere in here a connection diagram for this guy. PIO, nope, don't need that. Different ways of hooking it up. Voltage regulator. So yeah, it's got an on-chip 5 down to about, it says 3.4 volt regulator. And that can provide the VDD signal, or VDD that it needs, and the VIO, and you just run your VBus in on the reg in there. And it does recommend some ESD and protection and stuff, so I'll probably put that on here as well. So we're going to want to tie, let me make a VBus symbol so we don't have to drag this all over the place. This will be VBus. And then we'll want to hook up, I think it's VBus and reg in here. Double check that. So VBus and reg in, yep. And then the output, we need 1 to 5 microfarads on the VDD output of the regulator. And then we hook up the VIO to that as well. We'll just call that VDD for this guy, and we'll have, whoa, not that. Drag the whole symbol down here and hook that in, that in. Let's take a look at that reset pin. I don't remember if that needs to be connected. Let's see. External pull-up is not required, but can be added for noise immunity. Well, an external pull-up's cheap, so we're going to add it. I think that goes up to VDD as well. Yep. We're going quick, so this is not going to be the world's prettiest schematic, but it's going to get the job done. Try and clean it up at least a little bit. Okay, and then I do want an ESD diode on my 5-volt in just to protect this guy. So I'm going to use, let's see. I think we've been using that guy on our 5 volts recently. So this will go on VBus here. And we're also going to need, we'll need some caps and stuff, but I think I'll drop those on at the end. I do have somewhere, let's see. This guy's going to be a little bit overkill, but he's already in my library. I'm trying to if I have another good ESD protection for like a USB. That one's not hooked up. Yeah, we'll go with this guy. He's way overkill. Where'd he go? That one. So this guy's a common mode choke with ESD protection built in. And we can put that across there. And we'll go ahead and hook up our USB lines. So we've got the plus, data plus goes across, data minus is here, and then N, P there. On USB-C, when you're the device side, you do need to hook up both sets here. And so that'll give us ESD protection. We need to put grounds on that. And we need grounds on this guy. And we'll load, let's see, a bunch of no connects because we're not using the other channels of this. If I was like building this for production, I would definitely there's a single channel variant of this part, but I normally have done designs with USB 3 where I have all 3 of these in use. So I have a bunch of these already. No need to go buy more parts. So I think that kind of covers that section. We do need some caps on this. So we pull this back up. They want, well, this is silly. We're going to use just one cap that's like 4.7 or something microfarad here. And then I'll see what I've got for voltages for a cap to go across the regulator input. And we'll need one on right by the USB connector as well. So see, we've got a 4.7 microfarad. Oh, I've got 2 of these. Which one have I been? I'm assuming I've been using the 10. Library's a bit of a mess. Let me double check this one. Assembly, looking for 4.7, 10 volt. Yeah. That will be this one. So we're going to put that on the regulator output. So that'll be VDD. This kind of more out of the way down below here. And then I should have, let's see, what package size was that? 4.7. That one's an 0603. I think I want a 402 right by the pad. So I've got a 1 microfarad of 402. So we'll use that on, that'll go next to the VDD pin. And then we'll have a second one that can go right next to the VIO pin, although those are right next to each other. Usually if I just do one small bypass cap per power pin, that's pretty safe. And then the VBus input looks like it's good with just a 1 microfarad, but I'll probably do the 4.7 as well on that because we've got the cable and there's not really going to be much more capacitance on here. So I'm just going to go ahead, duplicate that block, and then make all these be the VBus. And now we've got caps for our VBus. So there'll be one that goes right near the pins here. We'll have the little bigger bulk one, the 4.7, then there'll be one that goes right by the input from the USB connector. So that should handle kind of all of the USB side of this device. Now we need to go hook up the other end. So these signal names for the UART were based on the direction from the other board. And so I'm basically going to use this board as the kind of crossover for everything. So the other board was transmitting here. So that's going to be the receive. So we're going to go kind of create labels and map this out. Actually, what I'll do to make this more clear, so I don't lose track myself. So that one, the data is going to be going this way because the labels were from the old board, and then or from the other side. And then this one, the data is going to be going this way. So we can kind of keep track that way. And then select that direction, we'll copy these and see if these all match up. So we've got, nope, looks like they're going to be backwards. So the TX one, yep, is going to be that way. And then that's going to be that way. And that should hopefully prevent me from getting these mixed up. Although it's UART, so we're probably going to mix it up at some point. But let's make some new net labels for this. So I'm going to do MCU RX, because this will be the data coming into us now, and that'll go there. And then MCU TX can go there, and then we can delete those two and drop those. And then we'll make the same set of labels for the console. RX comes in, and then some console TX will be the one coming out. Yep, so we transmit out, and then we receive coming in, and here we transmit out and receive coming in. And now we should be able to match these to the pins here. So let's see, the TX pin is an output, which is the output here. So we need this TX to go here, RX to go here, and then TX let's see, I can hit Y to flip those that way. There we go. Those should match. And then I want to check and see what this thing recommends doing with not used flow control signals here. On the UARTs, contains 2, RTS, optionally the other modem control. UART program to support a bunch of different stuff. Okay. Let's see. That's not what we want. Flow control. Utilize the functionality must be configured to use hardware flow control, which we don't want that. I do on the old board that we used. Looks like we just left them disconnected, so I think we can do the same here. So these will all just be no connects because we don't need flow control. That pin I think is already, what are its other options? Yeah, that one's just a no connect. I don't think we needed the VPP function, though I will double check that. Oh, that's in case we want to reprogram the interface. That might actually be useful. So we can put a 4.7 microfarad capacitor between that and ground, in case we want to like flash a different vendor ID or something into this. Okay. So that should take care of hooking up the UART signals here. And then last is just to hook up the, I guess we have power and the ARM debug adapter. So just, I'm gonna, now that we know kind of the size of these, do a little rearranging. So we can kind of tuck our caps in a little closer to this block. And then scooch this guy over here. Get him out of the way. Then bring this guy nice and close, and we'll get it all hooked up. So this is basically just passing through all the signals here. So we're gonna kind of start at the top and work our way, I guess at the top of this one, not necessarily the top of the other one here. Trace is SWO. SW clock goes here. And SWDIO goes over here. And let's see, the TDI is no connect. We're not using JTAG on this, so put a no connect there. And then key is also a no connect pin, I think. Let me double check that on the mating schematic for this. Yes, key is, and I don't think we're using ground detect, and then VCC just needs connected. Perfect. So the VCC will be the regular 3 volts, or 3.3, not the switched one. Ground is connected to ground here. And then we'll just mark the key and ground detect as no connects. That handles that guy. Drop that down there. He is also going to need a cap next to his power. Anytime we got I/O going in and out, always good to put a capacitor nearby. And then last, I think we just have power and a couple more caps. So well, I've got this bypass cap here. We're gonna need one of these over by the SD card for the 3.3 volt switched rail. And then we're going to need one of these where the power comes in here on the 3.3 volt switched, and one where the 3.3 volt comes in. And then we also will need bypass caps on the 24 volt, but we can't use these because they're only 16 volt. I put the specs of the cap in little tiny text inside them, so I can zoom in here. Oh, yeah, good question on why I'm using 1 microfarad for bypass. There's a whole bunch of folks have kind of written about this. I think there's a paper out there. It's like the myth of 3 capacitors, where people always talk about using different capacitor values as being a good thing, but that actually just can kind of create resonances and weird problems. What really matters is the inductance of the capacitor. And so I can get a 0402 cap. I don't want to go down to a 201 because it's kind of a pain to assemble. So I can get in an 0402 cap, you kind of just want as much capacitance as you can get. So I've settled on 16 volt 1 microfarad. That's kind of a good middle ground for getting quite a bit of capacitance, but still being able to put on most of my voltage ranges. When I get to this 24 volt bypass cap, that will be a 0.1 microfarad cap because I need a 50 volt capacitor for that. For some reason, yeah, so I've got no 402.1 here, but that's where I use I kind of just go for having as much capacitance I can in the smallest case size that I can, taking into account the DC bias derating of the caps as well. Because if you go real small, yeah, you can get like, I don't know, probably a 10 microfarad cap in an 0402, but you're not going to actually get much capacitance when you have very much voltage applied to that. I also usually try and go with at least like X6S, X7R caps, that sort of thing. So yeah, I use the 100 nanofarad where I need higher voltage, but on lower voltage stuff, I'd rather have more capacitance. I did a design. Actually, let me go pull up. I've got a microcontroller on this guy that I can show, where it's an STM32, and they wanted ST's guidelines for this show putting 0.1 microfarad caps on all the bypass, and then still adding like an extra 4.7 microfarad cap, which needs a bigger package, but I can get actually more capacitance just with 1 microfarad of 402s than the 4.7 microfarads add to it. So then I don't need to put the 4.7 microfarads on the board at all. So yeah, that gets that guy hooked up. I do want 24 volt cap coming in here. Not sure if I want, debating if I want to put an ESD diode on this input or not. I can always put a spot for one. I don't have to place it. We don't need it, but it's probably not a bad idea. So if I find, do I have a 24 volt? No, I have a 36 volt. Bidirectional ESD diode. Yeah, what's your voltage on those 22 microfarad 0603s? I'd be curious how much capacitance you actually can get out of those. We're gonna do that. I'm gonna label this guy as disconnected there. So that gives me some ESD protection, kind of just in case somebody bumps that guy. Okay, so you got a 3.3 volt rail at 6.3. Actually, well, let's go pull this up. So if we do what's real key with this for capacitors is to check how much capacitance you actually get at that DC value. So if I grab, I'm just going to go grab a pretty generic, if I grab the GRM series from Murata, which is kind of their consumer line, and let's see, 85, nope, not the high dielectric. And we grabbed, I think an 040, never remember the metric to case size conversions here. But if we grabbed I think it's a 105, it's a 0603, we grab a 6.3 volt, sort by capacitance, so I get an X5R cap here. I mean, they're already saying these get derated anyways. So yeah, like if you take your 22 microfarad 0603, by the time you put 3.3 volts in it, you've lost 70% of your capacitance. So you've only got really like a 6 microfarad of actual capacitance there anyways. So that's kind of the real trick and danger of ceramic capacitors, where you sometimes need to go to larger case sizes, is this DC bias curve gets real nasty. And you don't end up with what you think is on there. And this is where, I don't know, I find this really hard with like app notes from manufacturers, where they just say to put so much ceramic capacitance on there, but they don't actually say if that's like the effective capacitance or the kind of anticipating derating for things there. So that's something to watch out for. And I've kind of, we have a whole I've kind of a chart of caps that I've put together, because I'm not sure I'll be able to pull it up, but I have a chart of capacitors that I've put together just as a like, okay, across all my designs, these kind of meet, or a good middle ground, so that I don't need to have like a million different capacitor SKUs in my library. So that gives me my 24 volts in. Got some bypass there. 24 volts go out there. And I think this will leave everything wired up. I'm going to run an electrical rules check, although it's not really going to help me with much, because it's going to say power pins are not driven, which makes sense. Oops, did I miss connecting something here? In, not connected. Yes, you are. I think you are now. Not sure why it doesn't think that's connected. Something like off grid? No. In with no connection to. Oh, I bet we have a problem with the symbol that I built. Let's go fix that. CP 2105. So I'm using the alternative part. No, that's a. Oh, does that not need to be passive? That should connect. Maybe I switch these. Let's make that VPP. Make it a passive pin, and then let's make the alternate a no connect. This is a bug, or if I'm just missing something here, but load in an updated symbol just for that one. That'll be fine. And let's see, so now in function, well, now it thinks there's 2 of the VPPs. What did I do wrong in there? Not change, update. Symbol attributes. try that. Oh, no, we're not simulating. I don't have model that. Rules checker. There we go. That seems to have cleaned it up. Okay, I'm missing the footprint library, which I'll fix when we set that up. And we just need to set up some power pins here because some of these guys are defined as power. So, since I don't actually have like a regulator with a power out, we're just going to grab the power flag and I'll just stick these up top here. We'll need a couple of them. And we'll tie these together. Yeah, I make all of my own footprints and libraries pretty much because we have kind of a company standard a little bit or just kind of preferences. So it's a lot easier to modify them if they're all our own footprints. So we kind of our whole library that we have is all built in-house. We don't use the built-in KiCad library. Although we sometimes do for like quick prototypes and stuff, but the one thing that's really limiting for us on the library side with like the built-in KiCad one is keeping track of all of our internal part numbers and stuff. So we have, oh, I need to tie this to a ground as well. It needs to have a power flag. Like you'll notice if I zoom in on these parts, we've got little internal part numbers on everything. So that goes into our inventory, or not inventory system, but kind of our product lifecycle management that tracks all of our parts and availability. It's not, I don't own the company, but it's a small startup. I was one of the kind of early engineers there. So we've got that should make my ERC happy. And it needs footprint for that, which makes sense because this is a new library. So let's grab manage footprint libraries. I just need to add the, not that way, add an existing, and we'll grab our Scilabs. Perfect. And that should fix that ERC error. Perfect. Okay. So I think we have a fully defined schematic here. ERC is clean. Let's see if we can get layout done real quick here. So we'll jump over into the PCB editor. Bring that in here. And before we get too far in, get our board set up. Completed. So under stack up, I don't really care about defining my full stack up, but this is going to be a 4-layer board. There's no way we're going to get those SD card signals over a 2-layer board. Copper finish for the rendering. Sure, Enig. Make it gold. Make it pretty. All this should be fine. Constraints. Let me just pull up my other board. I don't want it quite as tight as this last one was, but we'll start somewhere. I can show just for what this guy hooks into. Turn off the planes here. Kind of, this is the complexity of the board that this is connecting to. So there's a whole bunch of stuff going on this board. I just want to pull my settings out of it. So constraints. Actually, I can think in mils better for this. So let me get, I don't know, the whole numbers are easier for me. We'll do I think 6 and 6 should be pretty reasonable. I shouldn't need 5 and 5. And then we'll do an annular width of 5 on the vias. There's not going to be any tiny vias on here. And then if I do 22, that would give me a 12 mil drill plus 5 on each side there. We'll go I could probably go down a little small. Yeah, we can go with big. We'll go down to like an 18. Oh, wait, no, that's not where we go. This is 4. And then if I do a 20, then now it's a 12 mil hole with a 4 mil annular. 20 mils should be fine there. Minimum through hole can be a 12 mil. Make these some round numbers. We're not doing micro vias. That doesn't matter. And then I'll set up a couple predefined sizes. So I did 6 and 6 for my tracks. So I'll give myself a 6 mil track. And then we'll give ourselves for power routing probably a 8. No, we'll need something bigger than that. I'll do a 10 and 20 just to give you some little bit larger tracks to get some power around. The USB I do want to do as a differential pair. I'm not really going to calculate out the impedance very accurately because it kind of doesn't matter. But I'll just do like a 6.2 and a 6 should be pretty reasonable. And we'll do like an 8 mil via gap there. And what did we say our vias were? We're going to be 20 and 12. So 20 mil, 12 mil hole. Don't need teardrops or length tuning. I will just make my default net class match what I set my predefined sizes to here. Grab a screenshot so I can keep track of those. Because I don't think I need. Yeah, that should be fine. Yeah, as far as manufacturing our boards, we've done quite a few different places. Our production boards are made, they're assembled up in Canada. We've got a shop in China that I think does the bare boards, but we don't really deal with that on our end. For prototypes and stuff, kind of depending on the complexity, usually I go like JLC or PCBWay. They are cheap and easy to deal with. PCBWay has a little more capabilities if I need kind of a fancier setup for some reason or something like that. But that usually works pretty well. Which this did remind me of what I'm missing in my schematic, which is that we need to add net labels to tell these that these are differential pairs. So if I go here, this will be USB EXTD plus. So I always use, we're going to be a little tight on space with that there. Let's do that. And add these in too. Yeah, this board I think will just go to probably JLC because it's pretty straightforward. That made a mess. Like they're definitely not the highest quality. I don't know. There's some stuff you don't get with like JLC in particular, as far as like high temperature materials and stuff, or at least you have to pay quite a bit extra for that sort of thing. This chip's just for protection. The filtering, this board, especially the serial monitoring, will be hooked up when I go do EMC compliance testing. So I actually don't care that this board itself passes EMC, but I don't want this board to be the reason that I fail EMC, because that would really suck to have an external part that's like not part of the product be noisy, and then I have to like filter it when we're in the EMC chamber or something. So I'm just putting protection on here so that when we've got this guy hooked up to the board, we're not gonna like fail EMC because of a dumb thing I did on uh, just the little dev board that we use to talk to our system. Yeah, we're really like other shops other than like PCBWay, or I think PCBWay does it more. JLC doesn't have as many options as like I think our actual boards we make out of either 370HR or iTech's IT 180A, which are like 180 degrees C glass temperature, so they do better through like multiple reflow cycles and stuff. They don't warp as much and they hold up better over time. Just thought I had set up 4 layers. There's 4 layers. Let's try 4-layer board. There we go. And then let's get our parts brought in. So we will close that, and there's all the parts. So this is hopefully a nice small board by the time we're done with it. I do want to kind of, we're going to go, let's see. So usually at this stage, I go selection filter, turn off all that, turn off all my silk screen. I really just care about kind of the courtyards and the rat's nest, figuring out how this is going to fit. And then I really only want to select footprints. So let's start placing this on here. The most critical signals, so this is where I always start, is going to be the SD card. Yeah, so this board is so we can talk to and kind of do manufacturing on that big board. So when we do manufacturing of the big board, we have to load a bunch of an image into the system on module that runs Linux. So that's what the SD card's for. Is you can boot off the SD card, load your stuff in, and then it's all running off the internal flash. And then we've got the debug console and stuff, so we can talk to things through there. So this was just like, these parts are all things we need when we're manufacturing the board and doing kind of production test, as well as some development stuff, but it's not stuff that we need when we're actually, once the board's in the field. So that way it just needs this one connector, and then it gets broken out to all these kind of separate pieces. When we built this board the first time around, we did it a little differently, and we had the USB to serial converter and the micro SD card socket on the board. Yeah, the big board is so we've got it's a safety system that goes on power wheelchairs, and so we've got it's got a microcontroller, a Linux SOM, and takes in data from a whole bunch of sensors and everything around it, and does a bunch of processing, and talks to the wheelchair and stuff through that. So it's kind of the it's roughly equivalent to like a Raspberry Pi with a beefy Arduino strapped on top of it, kind of as far as what we're looking at, but all kind of more bespoke for exactly our application. So it looks like here the SD card pins are going to be on the bottom section here, and I don't want those having to go under. They are, of course, going to cross over a whole bunch, but that's going to be kind of unavoidable. The UARTs are up towards the top, so we'll put our UART pins. Our UART chip up here. Let's see, flip the USB, so it's at least going out that direction. And we'll drop that there. Our little filter IC goes that way, and of course I had a 50-50 shot on whether or not that was going to cross over, so we'll go back to the schematic, and let's see what's going to be the easiest way to rewire this. I don't really want to flip. Let's do it this way. Pull that out. that back in, take this and flip it in that direction. Not like that. And move it there. This is probably not how I would do this on a production schematic that I cared about, but it's gonna do for now. Drop this here and hook our grounds back up. So much of getting layout right is all just about making changes back on the schematic that like make your life easier. So now those go straight through and don't need to change layers or do anything tricky to get to where they need to go. What else we got here? Yeah, being able to select parts kind of on the schematic and the PCB is great. The cross probing, so I'll use that here because I know I need like this 4.7 and the 1 microfarad need to go over here. You can also hit once you have them selected, the P key is pretty handy because if you've got them scattered all over, it'll grab them as one bunch of components. So like these ones are not next to each other here. If I hit move, they're still spaced way out. If you hit P, it'll grab them and kind of bundle them together. And then we know these one, let's see, the V bus, you go by the USB. And V bus will go there. Should probably do actually a second V bus connector or a bypass cap on the USB connector. Reason for that is the way these USB-C connectors are done. They've got power pins on each side of them. So that'll let that hook together. Should have our resistors and our ESD diodes. We'll grab those. And I want to hook these guys up. I'm trying to get the little CC pins out of these in a way that doesn't suck, as always. USB-C was built to be small and built to go into phones, and so it's not super nice for like kind of more rougher layouts when I grab the full the connector with all the pins on it. Let's see. And our ESD diode, that'll probably be fine by just one of them. If we've got capacitors on everything, they'll soak up quite a bit of that. Actually, the other way is I could just run this around. Maybe we'll do that. We don't need this extra cap. Go around the backside. Yeah, I think I do have my rat's nest size turned up a little bit. It's kind of a tough trade-off on some designs between turning up the rat's nest size to be readable and turning it up to where when you have a bigger design, it covers up like everything left on the board. Okay, so what else are we missing placing? We've got that. There we go. And sure we got these. Oops. Select the whole part. There we go. P, those all go around that guy. Other thing that usually makes life easier is I know ground's going to get hooked up at the end. So it is possible to go in and turn off the ground rat's nest. And then I'm going to go in here and I like to make my ground pins a green. So you go there and then turn on net colors for everything. Now I know what's ground and what's not, and ground doesn't mess with my rat's nest. Because ground just everything gets punched through via the inner two layers will be ground on this board. Okay. Moving on. We've got this set here, so we'll grab that. The barrel's gonna come in there. We'll have our ESD diode. Sit right next to that pin, and a capacitor can go right after it. And that'll just be a straight trace there. This guy, I think's gonna sit down here. Let's see how big this board's actually turn it out. I mean, I think we've kind of got a form factor. The SD card works best if the edge can hang off a little bit off the board. I don't think we're gonna need that. Can go back a little bit, and then yeah, that should work. Let me draw a board edge and see what this looks like. What are you saying? I should flip this SD socket? Let's get our edge cuts drawn. Just so I can draw these slightly more reasonable. Have the board be some increment of millimeters. Of course, it's going to give me the dimension in mils. What are we here? 50 by 60. Well, that doesn't need to be that big. I think we can make it. Oh yeah, this guy? Yeah, that probably goes better. Let's see if there's a... Once we route that, I'm not sure exactly which way those signals will want to go. But that probably will work better because then the connector can come off the front this way. Let's just see what things are looking like here. So we've got the SD card, which sticks off the edge there. He can go closer to the edge, so I can pull this whole edge in. I think if we do something like that, let's turn that back on so I can grab this. Now we've got USB there, barrel plug there, SD card will fit there. This cable comes off above. This guy will loop over that direction, and we just got to fit some caps and stuff on here. So I think we're in pretty good shape. Let's see, where do you go? You went with the SD card. Ideally, you would probably go on the back of the SD card, but I'm not making this a two-layer board. Let's get our grid size turned back down. To the side or underneath? Put you off to the side. And then we'll just route the power on the front there. Not great, but it'll work. Got our MOSFET and resistor here. So those guys can just go in between. Where's that chip detect? Oh, it's way up there. Sneak in somewhere. Put a resistor there for now. This guy is the pull up on the card detect. She could just go. All right, there's not too bad. Microfarad, you go is I'll go on the connector here. So we've got the 3.3 volts. Put that there. We've got the switched. That one can go there, and the 24 volt one can go right there. Awesome. And what else? One more cap floating around. Where do you go? You go next to that. The arm header. That's an easy enough spot right there. Alrighty. Looks like I can probably shrink this whole thing in. Oops, let's do it in full millimeter increments. Drag that in a little bit. If I rotate these, we could go even a tiny bit smaller. That's probably a good place to leave it. Top can go down a little bit. Oh, we need to get these cap pieces put up here. So we've got this reset that just goes to VDD. So that can go there. Got this cap that goes onto the PPP pin. And then we've got this cap, which will go on VDD there. This one as well. And we'll try and leave room for the USB to sneak through. And then we'll put the bigger cap right there. That's looking in pretty good shape. Where's VBus come in? Up top here. Oh yeah, never let the silkscreen dictate stuff. For like bypass caps and stuff, I usually turn off the silk on a bunch of stuff. That's why I do all my placement with it off, and then usually at the end, or at least once I have parts placement done, I might go turn it back on and move silk around. But I don't think I've painted myself in too bad of a corner here. Like these two caps, they don't need silkscreen. If they don't have silkscreen, it's a bypass cap. The pick and place doesn't care where the silkscreen is. But I think with that, we're probably good. Start routing. Let me squeeze this top edge of the board down just a little bit. So what have we got this down to now? We're a 41 by 45 millimeter board. Might give just an extra bit down there. And I do think I've got room for it. I'm going to tack a couple mounting holes on this just in case at some point we need to screw this thing down to something. Oops, that was not the button. What have I got? 2.7 millimeter, 2 millimeter. I think our 2.7 is probably what I want. We'll see if that looks huge once it's on the board. Those will also give me a spot if we need to ground this to something. At any point we can do that. Let's pull those in. Probably won't need test points. There's test points for most of these signals on the other board. And like things like this SD card, like if I've got to put a test point on that, something's gone pretty wrong at that point, I think. These connectors too, I have a set of like the PC Byte probes, and so it's pretty easy to drop those probes onto the pins of these connectors, which is mostly where if I needed to probe something, I probably would. Yeah, I can use the mounting holes as a ground spot if I need to put a probe on it, or if I need mounting hole ground or scope ground. Power, I really don't hope I don't have to probe. There's a bunch of power probes on the board that generates the power, and I'm kind of trusting that the regulator on this thing, being a linear regulator, is just going to work. So I've used it in the past and it works pretty well. So I think we're probably ready. We can route. So if we now go tracks, pads, vias, turn off graphics, start routing here. So let's start with the SD card because I want to try and run that with as few via transitions as possible. Let's get that down to a smaller grid. Are these going to all need to go onto the back? Well, if I can get the clock through, that's the worst one. And then everything else can kind of... Grid's being weird here. Let's just go tiny. Yeah, we'll get the clock tied, and then the rest of these are going to need to punch through to the back anyways. So if we do my normal kind of XY routing, that would be like this. Try and use the bottom as our horizontal where we need to for these SD card signals, and the top layer as our vertical to get where we need to go. So this one will come down. I left enough room or not. Punch through there. I don't really want to paint myself in the corner there, so this will go on the back too. Yeah, this is going to be a fun little... Probably made this tighter than I needed to, but I think we'll make it fit. And let's see, this guy... Gonna go through there. That's where I wanted it. Yeah, I've never tried the free routing stuff for these sorts of designs. I haven't really needed it. Routing's kind of the fun part for me anyways, so... Let's see. I already don't like where that's ended up. There we go. Spot for my vias. And have I gotten myself into trouble here already? Looks kind of that way. This one needs to go up there. These will be 50 megahertz, I think, is the clock on a SD card bus on our system. I don't know, SD can run at quite a few different frequencies, but I think the way this one's configured, I think it's a 50 megahertz. So they are pretty high speed. At least high speed enough that we're going to be careful with them. Let's get a little more space through here. Via, yes. There we go. Now we're out of trouble. I hate it when the router does that. There we go. Get the little goobers out of there. And I think looking at this, yeah, so I'm not really paying too much attention kind of from an optimization standpoint for these. What the main thing that I'll have to do is both of the inner layers, since this is a 4-layer, are going to be ground because you need to have your signal kind of right above a ground plane, and you need to have places for it to transition between those layers. So once I get the ground planes in next to each of these places where we transition from the front to the back for these high-speed signals, I'll go put a via between the ground planes that ties those together. And so that'll let the fields pass between the two ground layers, because otherwise they kind of spread, and then that's where you can get a lot of noise problems. You can also get crosstalk problems from there. So as long as we've got a transition via for all of these, we'll be in pretty good shape. We don't really have to worry too much about like impedance matching and stuff at this frequency. Is not, for what this is doing, is not going to matter a whole lot. But the making sure we've got good return paths for the return current is definitely going to matter a lot. Otherwise, I'm mostly just doing any board I do, aside from a few kind of select signals. I try and do like here, most of the red signals are going vertical and most of the blues going horizontal. The clock, I don't really have any signals that need to cross here yet. So the clock, I'm trying just to keep on one plane, not have any transitions. Vias at this frequency aren't really going to create reflections, so having extra vias is not going to be a big issue. It's just making sure that the ground plane or the return currents have a place to go is a much bigger concern than the vias themselves. It's not the via itself at this frequency that really causes a problem. It's the ground return current not having a good path back home, because every bit of current that goes one direction has to flow back the other way on the ground plane, or at least it has to flow back the other way somewhere, and you want it to go on the ground plane and not end up places where it's not supposed to be. Let's see, so then let's get power hooked up here, and I think that's the SD card interface, card detect. So let's get that. Do we have anything that needs to run through the middle here? No, this can just stay on the top layer. Normally I'm a lot more diligent about my kind of north, south, east, west routing planes on a board, but for this, I don't really have a whole lot of, there's a lot of space on this board. But we will need to go, and kind of part of the reason we'll be able to see here for choosing to do the kind of my east-west routing on the bottom layer is so I can get underneath this connector. If I did my across routing on the top plane, I'd get stuck anytime I needed to cross the connector here. I'm working down. Let's see. So power. I want to scooch this guy a little closer. And let's figure out where this needs to go. So that only needs to go just down there. Probably doesn't need much of a wide trace at all, because it's just telling the debug connector that it's hooked up. So we'll go there. Like that. Let's start down here and see if we can hook these up. Guessing these are gonna get kind of messy. Let's move this cap out of the way because he's in a routing lane. This guy might be a problem with this boot coming through here. Actually, Will the via fit underneath? Oh, it will. Let's do that. Select that. Let's just kill a bunch of that trace. We're going to run this a different way. That'll work well, I think. And then before we get too far in, I'm going to pop some ground vias out of these guys. Don't think, no, not doing via and pad on this because that's just a 4-layer board. That's a luxury we don't need. I'll make sure I don't take away all the space I need for these vias later. There we go. Okay, so now if I go and pull these up, let's go down to the right size track. There we go. Hopefully we'll be able to see where these need to go a little better. Okay, so the MCU reset is the bottom one. This might actually work. Ooh, these are in order. Well, that makes life real easy. We're just gonna need to nudge this out a little bit. Might give my board an extra millimeter here on the edge. Oh yeah, that's a lot of space. No reason to squeeze these guys together too tight. And that can go there. And nope. Oh yeah, I tried. I'm trying to remember which tool it was. There's a company out there that's got like an AI router that plugs into KiCad, or you upload your designs to it, and it promises to like AI route. And I tried to use it a while back just as like a test. And what I found really funny was like I don't even know if the routing was good because I got so annoyed that they couldn't figure out how to make they like focused on the AI routing part and not the like, oh, which capacitors go with which ICs for decoupling. So it was like you had to go through this whole interface that was like telling it like, oh, this capacitor needs to go next to this like IC. I was like, you should be able to figure that out from where they're at on the schematic. Like I don't need to hold your hand through that. So I kind of gave up on it. I was like, that's taking the fun part of routing and replacing it with tedious, like annoying stuff. I do think definitely some of this has some like some of the paid like Pro Tools. I've seen some people use Siemens pads tool, and it does actually have an auto router, but that's not the part that I think is like cool with it. What's really cool with it is it has a lot more like it has a feature called like sketch routing. So like you could have selected like a set of these and been like, oh, I kind of want them to follow this path, and you just kind of like draw a little line, and it can take like 10 nets and just like route them kind of following your line, so you don't have to like manually go in and route those through. And like that's a really cool like time saver feature that they've implemented in there. Like I really like if seeing that, and like that's really cool. And I think a better like I don't need the AI to do the full thing, but like tools like that where it just increases your productivity but still gives you control over what you're doing with the board, I think is like way more useful than like AI routes full board, because that's a lot harder problem to solve than just, hey, how can we make something that like intelligently kind of helps do the minutia or like helps make the tracks a little smoother and stuff. Yeah, exactly. Like Copilot and code. Like it doesn't need to write the whole code for me, but if it can help do some autocomplete so I don't have to like think through the boring boilerplate, like that's great. Let's see, so this switched needs to go there and needs to go there. Well, that's kind of a messy place for it to need to go. Okay, I know how we're gonna get that there. Let's go to the back. Run underneath. That's making me rethink where I want my capacitor now too. But that's okay. What do I got? Oh, this guy? Yeah, that is pretty annoying. Let's not do that. But not like that either. That's worse. Oh, it didn't snap to that pad. Aha. Let's do down width. That's much less crazy. Can clean that up. There we go. Oh, that didn't clean anything up. That made it worse. There we go. And then, yeah, seeing how I've moved this, I think I want my cap to go there. And then now this guy can just sneak on over here. To be that wide. There we go. Like, this is where I want, like, give me AI, or like, not even AI, just like make the router smarter so it doesn't make these stupid little corners. Like, that would be useful. Okay, and then we need this to go over there. I guess we've already got, can't get a trace through there anyways, so that can go there. Yeah, give me better KiCad. I don't need the full AI. I just want make the tool better. Which I haven't done any contributions to KiCad's to the layout part. A while back I did contribute a few things to the symbol table on it to make that a little nicer to use. It's been a few years since I've gone spelunking in the KiCad code base though. That looks pretty good. But for that, it doesn't need to be that big of a trace. There we go. Okay, so now we've got that guy's routed up to do USB, which was gonna be fun. So we got VBus comes through here, sneaks out, and then I'll go up a width through there and through there. Yeah, all of KiCad's in C++. There is you can do plugins in Python with it. And then there's also they've released it for the in version 9, which is what I'm using, they have an IPC backend for that you can have other programs talk to it. So you can make a script or something talk to it that's a little more separate than their old plugin interface used to be, which has some pretty cool features. I haven't played around with it, but that would let you write it in kind of any language that you wanted. I think somebody's got like a Rust plugin or something for it, which would be my language of choice if I was going to dive in and do a bunch with their IPC interface. and they're supposed to have that come out for the schematic, I think, in version 10 next year. So that'll be cool to kind of see what people do with that. It'll be a lot more stable interface because the KiCad normal IP or their old plugin interface was basically just like swig to that the Python could call, which is all fine and dandy until it's just swig, which means that anytime somebody changed a C++ function, it would break everybody's plugins, which is not really what you want. The joy of these crossover USB-C connectors. You always have to do something ugly to get both sides connected. What are we missing here? I think that's it. Let's see if the diff pair is set up. Oh, it mostly is. I nudge this guy down so that these are more straight. Just because I'm OCD like that. Doesn't want to let that connect. That's okay. Well, that looks like junk. Let me try poking out from here. Thought I nudged you so we wouldn't have this problem. Let's undo. Get rid of those. Yeah, I write a lot of C++ and Python. They're both fine. I find myself, I've been using Rust more and more and liking it more and more for the stuff I'm doing. I feel like it's got kind of the ease of use and honestly, like, yeah, it's a little harder to learn because it's got the borrow checker and everything, but it's got, once you get the borrow checker figured out, it has kind of the ease of use and like foolproofness of Python. Because the borrow checker means you don't have to think about as much stuff because it'll just tell you if it's wrong rather than like, oh, it broke and segfaulted at runtime. Combined with like the speed and performance of Python. Like, I'm not going to write a web server in C++, but then if I had to write a web server in Python, it's going to be slow. And I do like a lot of this stuff I do is embedded Linux where I'm pretty resource constrained. So like Rust kind of gives me a nice like middle ground of it can be really fast, but still actually pretty approachable and like easy to write the code. And you got really good libraries and can work really fast in it. You know, it's fun to do things wrong until you end up like, was it a while back where I was just like, our main code base is C++, but I've wanted to have like a counter that's like it's been X number of days since like Rust would have caught a bug that I wrote because the other day I had implemented a new function and just in typical C++ nonsense forgotten to what did I forget on? Oh, forgot to actually like specify forgot to actually return a value. Like it's a function that returns, but I forgot to actually like call return at the end of the function. And it takes like on embedded stuff, like we run the optimizer pretty heavy. So it takes a good like several minutes of like building to get the code on the board and everything. And go to launch it and then it like seg faults and okay, you boot up GDB and figure out what you did wrong and then realize that was what you did wrong and it's another 5 minutes around that loop. Which like yeah, I could have had warnings turned on in my compiler that probably would have caught that, but they were probably covered up by some other warning because there's a lot of warning. Like we try and keep the warnings down in the code base, but you can't always keep the warnings down in the code base. That V is a little close. Stop snapping. There we go. I found especially in the like really embedded space on like microcontrollers and stuff, Rust has been super nice because you don't. Oh, that didn't need to be power up there. That's why that was so silly to route. That's just a pull-up resistor. Let's do that. Something the right size. There we go. On microcontrollers, we've been playing around with it on the STM32. We've got a new product that actually the board that this is hooking up to, all the embedded microcontroller codes all in Rust for it. we've been using the embassy stack and everything, and it's kind of like having an RTOS, but without some of the like overhead and annoyances of having an RTOS, which is a pretty cool kind of programming paradigm. Yeah, we do a bunch of computer vision. Our computer vision stuff is C++ for a bunch of reasons, but that kind of OpenCV and the stuff that we've used that for, and we use stereo depth cameras, and so those all are C++. So our main like algorithms and everything are C++, but then we've got a whole like networking program, and so that we've used Rust for all of our like cloud communications and stuff, and been really happy with that. Because the Python was too slow for it. But yeah, I'm not going to write a thing that has to talk to like 5 AWS services in C++. Like that just sounds like a nightmare. That hooked up. Oh yeah, I'd teach Rust before C++ these days, I think. I'm a better C++ programmer because I learned Rust. I don't know in which order you teach them, but like thinking like, oh, I need to make the borrow checker happy, so you can't go off and send a like reference to something to another thread, because that's just like not allowed. Like C++ will let you do that, and then you have to be very careful with it. Whereas instead in Rust, I'm like, oh yeah, you'd have to wrap that in a mutex, or you'd have to do like something so that it's safe. And so I think like just thinking through like how to make that work in a lot of my Rust code like makes me think, like I also think about it when I'm doing C++ code, and really care about like ownership of like, okay, who actually owns this memory, who created it, who's freeing it. um do I have like, is this thing like thread safe, that I got back from this API, or like is something going to go jump on it later? Like Rust gives me all those guarantees, and like I think through that now when I'm doing C++, of like, do I have that guarantee on this particular thing I'm working on, or not? That's one of my things with like OpenCV that I find really challenging, is some of the like the ownership semantics over like buffers and stuff in it are like not super well documented or clear in it. And it's so like with Rust you kind of get that just as part of the compiler contract of like, okay, this, if I'm getting back a reference to something, then I know something else is managing it. If I'm getting back the full object, then like, okay, I own the memory. I'm curious to see. My wife's going back to school for computer science, so we'll see if she one of these days I'm gonna drop Rust in her lap and see what the heck she thinks of it. But she's too early on in the program for that. Yeah, some of the stuff is reference counted. It's just when you're like getting raw buffers out of things, sometimes it's a little unclear who owns it, and it's not necessarily that it like is or isn't. It's that like in a lot of cases we were just trying to find the docs of like, okay, do I need to clone this thing before I pass it to another API, or can I like keep it? Um, do I have full power over it? And it's just like not super clear, especially from the docs. You know, like spelunking in the code to go figure out the ownership of something like that. I think aside from ground, we might be routed. So let's get ground hooked up. Go back to our big grid and going to put some zones on here. Not dimensions, zones. So this will be ground and clearance. It's going to be back in millimeters again. We'll fix that in a sec. And let's fill those. That's massive clearance. We don't need that much. We do want thermal release on through holes. All the surface mount stuff's getting reflowed, so actually there really aren't any through holes on this board. This whole thing's getting reflowed. And then we'll make this like 10 mil clearance, 8 mil minimum width, and refill that. That looks a little better. Should give me a nice solid ground under everything. And then last thing we need to do is just go add, I was talking earlier about those stitching vias, so we need to make sure that, actually I might just stitch the whole thing and then I'll put some around the right places. So while I've got the dense grid, I go to like a 2.5 millimeter grid to just, and then we'll just give it every 5 millimeters around the edge of the board. Sure our ground planes are good and tied together. Already kind of one there. We'll need a different grid to get that edge, I think. I have room to sneak some on the edge here. I don't know if I really want to collapse these guys too tight. I might just, hi. Collapse these in. Actually, down with there. Let's just break this. Pull that in. That'll shrink the area a little bit that we need those for. See if I can tuck a few in here. Yeah, the APIs, there is a lot of like C in those APIs, which like, I don't know, mixing like C and C++ is like the worst variant of, like they're kind of the same, parts of them are the same language, but there's a lot of it that is very much not the same. They have different paradigms, despite being mostly compatible. There we go. So now I've at least got a ring kind of around the edge of the board. And then we'll go add, looks like we're missing a few vias on, or traces on the top here. So let's get those hooked up. Use a bigger trace. There we go. That guy's hooked up. And we need via there. This is the other feature that like pads has that I wish that KiCad did, is you can like tell it to go auto break out all your caps and it'll go auto put all these vias in. Hook that straight through. I guess I could just flood the top of this board too. We still need to get all these hooked up, but that might be, make another plane and put ground top and bottom as well. These guys hooked up. let's see, 7 unrouted. Let's turn on that rat's nest for our grounds and see what we're missing. So that one. This guy needs just vias stuck in the middle of it. Let's go something a little bigger. 1, 2, 3, 4. Get there. And we're down to 4. What else are we missing? One there. There's something still unrouted. What am I missing? Let's hit the DRC and find out. Unconnected. Oh. Background. Yes. That one. Sure. Oh, yeah, there's not room under that for my current vias, so these will just poke out the sides. There, it's saying no unrouted. What do we got for errors? Violations. Clearance violations. Oh, that's kind of funny. Okay, so 6 mils is not my min because this BGA pattern is tighter than 6 mils. Let's go fix that. Constraints. Min clearance is now going to be 5.5. So yeah, usually on a bigger board too, and like I've got the grounds here. Usually on a bigger board, I'll also go highlight all of my power as. Oh, it's complaining about the net class as well. I'll go highlight all of my power stuff as different colors too. Like I'll use like orange for one power net and yellow for another or something like that, so I can tell where all my power signals are going. Let's see, we're down to 2 errors. So we have board, which, oh, this footprint always throws it because there's a route in the board and it thinks that the board edge is too close to it. Which that's not really the board edge, that's just a mounting hole. So those we will exclude and exclude. And I think our warnings are just silkscreen at this point. So that's doing pretty good. Let's get that top solder mask, or not solder mask, top plane put on here as well. Do you want copper and bottom on the top? So, oops, not on non-copper. Let's start there. Around, front, bottom. I do want reliefs, I think, on all of these. They don't need to be that big, though. And that, close the outline. Fill, so now on my top and bottom layers, that gives us full copper. And I think I just need stitching vias. So I need one tuck to there. See if we can sneak one there. I guess those really aren't sharing that one because there's one there as well. One there. Via there. Kind of already got one there, but we'll sneak some around. And via. Put some around this guy as well. Not that these UART signals are going to be particularly high speed. But extra ground vias never hurt. You want to make sure that gets hopefully a little extra fill under there. I don't know what that's really going to do, but put a via there, on there as well. And if we refill zones, that should go in pretty good place. I have red arrows from the DRC now. There's no errors. Oh, I got one. What did we do? Oh, it's now complaining about a via being too close to the board edge, which I, again, don't care about there. Oh yeah, there used to be a plugin that would do via stitching. It would just go put a grid over the board of vias. But I think last I tried it, it did not work with V9. I'm not sure if that's been fixed since or not. That's one of those ones that probably needs to be rewritten to use the new interface. Let's see, I think we could do silk screen now. So for silk, I want to turn off outlines and don't care about back copper. There's no adhesive on the board. I actually don't really care about front copper. I really just care about my part outlines and my... Oh, this is one of the ones that's annoying because KiCad doesn't let you move the pin 1 indicator of the part. So I guess we're going to scooch this part just a little bit. Get it out of the way of that. There we go. What are we doing here, track? There we go. Got that one clean. Let's select text, not any of these. C10, what are we doing? There we go. A31 will be fine there. Move C11. Yeah, the 3D view can be pretty helpful for finding islands and weird stuff as well. I always have to go back for it for my like sense of scale too. 1 C7 R1. That looks pretty good shape. C6, get my diode. Yeah, having a second monitor up helps a lot. I do that too when I'm like cross probing on the schematic and stuff. Usually it's just a little hard to stream 2 monitors at once. That guy almost has room there. It's a little awkward. We just do a leader line on these. Meters. What do we select here? Thin. Yeah. Nope. 0.15. There we go. Put those. R5 can go right there. This one's messy. J2. L1. Those I know hang off the edge of the board on this particular footprint if you put it in that spot, so that's fine. Before, make these upright if I can. And I think that's going to be clean. Let's see what we got here. Or warnings just of the silkscreen hanging off the the board edges. Oh yeah, I could definitely run like two sources and stuff. I would just forget to switch back and forth between them. It's not a technical limitation. It's a me limitation. I think that pretty much defines our board. So if we go take a look here, yeah, we got copper pretty much all the way. There's, oh, it's just doing funny business. Which plane was that? Top plane looked really weird. Oh, there's a little gap there. Let's do a little sliding around to this track. There we go. That makes that actually connected. Try not to leave too many islands. Get the bug off of me here. What else we got? How's the ground plane? I mean, that plane looks perfect. No notes there. That one should be good. On the back, I don't know if I can get this to, oh, maybe I'll get this to fill in between. Let's see here. Oh, because we got, that would have to scooch. Does that fill? Where am I even trying to fill this? I'm losing track of where I'm at. Oh no, it's that one that's too tight. So I'd like there to be ground in between these, but that may just not be possible without moving a bunch of things around that don't matter. So those two might just be the way they are here. I probably won't put the channel name on there. Actually, that is a good reminder, though. I need to put our company name on it. Let me find... We have a symbol for this. We just have our logo as a symbol to drop on the schematic. So that'll go on the silk screen. Somewhere. Where'd it go? Oh, 0 is like not where it should be on this guy. There we go. I'll just put that. I'll have to go into our company system and go pull whatever part number this board's going to be and get that dropped on there before I send it to Fab. But I think that's going to be our board. Oh, there's a bunch of things turned off. That's why things look a little weird. What's turned off here? Board body's off. There we go. That looks slightly less strange. And the silk was off. There we go. So yeah, got our USB, a little SD card, power input, header to plug our programmer into, and then this will go off to the main board. I think that's probably going to be it for today because it is about dinner time here. And I feel like we got this guy, that's kind of end to end. I guess I'll do, there's going to be a few more changes that I make and stuff, but I'll show if I was going to send this to Fab. I'd go in here and create a output directory and go in here and include these layers, paste, silkscreen, mask, edge cuts, and plot these out. I know every shop has like different units and stuff they want, but I think usually this gets it. So you can go plot, and then I'd go generate my drill files as well, which folks will have different, yeah, obviously things here. Generate that. Actually, the other thing I did forget to do, it's helpful, although it doesn't, some places it doesn't matter. It matters some for us because we have our own little pick and place machine we'll build, is making sure that my origin, you can set where the origin point is for everything. So this sets that's the 0 point for my drill and XYRS files and stuff. Yeah, some PCB companies have their own like JLC and PCBWay do. That is a good point. I don't end up using those because a lot of times our stuff goes off to kind of more traditional shops where we still just email Gerbers back and forth, which whether or not that's the best way of working. The other thing a lot of shops have started doing is I haven't done it in KiCad. Yeah, KiCad output OBD++, which this is like one file that has the whole board in it. And some shops prefer these. They're a little less interpretive as far as ways they can mess them up. These are also what you would feed into like some EM simulators and stuff use ODB++. So that's become a lot more popular for fab output from, I've at least had a couple shops ask for that in the past. But yeah, I think that's gonna do it for today. So I'm gonna go ahead and end the stream here. Thanks for anybody who stopped in and was watching. And if you're watching this in the recording later, if you got questions and stuff, drop them in the comments down below. Thanks, everybody.